Good day and welcome back. This will be our first of four videos discussing vectors. And as many of you have encountered vectors probably at multiple times in multiple different courses, think of this as a good opportunity just to introduce kind of the associated terminology, notation, definitions associated with vectors, and really just an opportunity to make sure that we are all on the same page as we lay the groundwork for what's to come throughout the remainder of this course. So to begin, a vector simply represents a quantity that has both magnitude and direction. And the common question I would ask you if we were face-to-face in class is, give me some examples or common examples where you've encountered vectors in other classes. And typically the responses that I would get immediately, we would think of a force as something that requires a vector. There's a direction in which the force is applied, and there's a magnitude, i.e. an amount of the force. Similarly, we think of velocity as something that requires a vector as well. There is the direction of travel, and then the speed, the magnitude, at which one is traveling. And to begin our discussion today, we want to look at the geometric perspective. So when we're thinking about a vector, we think of it simply as an arrow kind of in space. And the typical notation that we will use is always a letter or representation, and a vector always will get an arrow over it. And as you look through the textbook, which I know you all will, you might notice that they don't use this exact same notation. Instead, the textbook uses bold font, but I find it very hard to use bold font when I'm writing, say, on a tablet or writing on a paper as you might be. And in terms of the vector itself, we think of it as having a starting point, maybe I'll call this A, and a finishing point, which we call V. So the notation we would use is V is a vector going from the point A to the point B. We refer to A as being the initial point of the vector. And for convenience, I will almost always use IP to represent initial point. You are more than welcome to do the same. We think of B as being the finishing or more technical terminal point of the vector, and we represent this as TP. And a few observations related to vectors. The first note I want to make is it turns out it doesn't matter where in space we sit a vector down. What it means for two vectors to be equivalent is if they have the same length and direction. So two vectors are equivalent if they have the same length and the same direction. And I'll also note, to kind of add on to this, there is only one vector that has no length or no direction, and that would be the zero vector. So the zero vector is kind of an outlier for us. We denote it as 0 with a vector over it. It has no length, and it has no direction. So to become more proficient with vectors, we want to talk about some of the basic operations that we can perform, namely vector addition and scalar multiplication. And we will view these operations from multiple perspectives, but to get started, we're going to focus in on the geometric perspective. And from the geometric perspective, vector addition, so adding together two vectors. How we go about this is if U and V are positioned so that the initial point of V is at the terminal point of U. All right, so let's get a picture to go along with these words. So we're thinking we have the vector U, and we want to position the vector V so that its initial point, so where it starts, is where the vector V finishes. So what we have in this diagram now is the initial point of U is at the terminal, the initial point of V is at the terminal point of U. Then U plus V is the vector which goes from the initial point of U to the terminal point of v. I think it's always more complicated in words, so let's get a picture. It goes from the initial point of u to the terminal point of v. But it is required upon having this configuration in the correct form. So to sketch u plus v, we simply put v so that it starts at the finish point of u. And maybe for obvious reasons, this is referred to as being the triangle law of vector addition. And an observation that's worth making here is much like numbers, the order we add vectors does not matter. That is, vector addition is what we would say is commutative. The order does not matter. U plus v will always be equal to v plus u. Okay, so the second operation worth discussing here is scalar multiplication. So once again, just kind of reading through in words, and then we'll follow up with an example. So the scalar multiple c times v, and it's very important to think of the quantities that we have. C is representing a constant, i.e. scalar value, and the v that we have is a vector. And paying particular attention to kind of the notation being used, i.e. the vector arrow over v, we see that it's a constant times a vector. And if I want to describe to you what this new vector CV would look like, I need to tell you what is its length and what is its direction. So its length is going to come from being the absolute value of C times the length of V. And this absolute value of C is really just ensuring that its length is a positive quantity. And its direction is the same as V if the constant is positive, and the opposite of V if the constant is negative. And I'm going to come back in a moment after our example and add in a few more details here. But in terms of illustrating this example, let me just note if we have a vector V, and I'm just drawing something somewhat randomly here, what I would like to do is think kind of first, what does minus V look like? Minus V, in this case, we're thinking our C value is -1. So the vector is going to go, because of the minus sign, in the opposite direction. And its length is going to be exactly the absolute value of -1 times the length of V. So the length is unchanged, but it now just goes in that opposite direction. Then if we wanted to sketch something like, let's say, 2 times V, its length would be twice as long as the length of V, but it would go in that same direction. So hopefully that gives you an idea of how we can think of a scalar multiple from this geometric perspective. The only other important observation to add on here is that there is this special case of a vector not having length or not having direction. So if C is 0, our constant, or the vector is the 0 vector, then the scalar multiple CV will also be the 0 vector. So let's look at one more example dealing with this geometric perspective. Let's combine ideas related to vector addition and scalar multiplication to sketch the vector u minus v. And the first thing I'm going to do is just give you a little bit of my intuition. So I'm thinking of this as u minus v. And how I'm going to think about this is, what would I have to add to u minus v to get back u? And hopefully what you're thinking is we would need to add v to it. So from a very intuitive perspective, I'm going to think of u minus v as the vector we add to v to get u. So from a graphical perspective, if we want to represent this, if we have the vector v and u, and we place their initial points together, which we can always do, somehow in this picture I'd like to get u minus v. And what we indicated above is u minus v is precisely the vector we add to v to get to u. So we want to start at the terminal point of v and draw a vector to the terminal point of u. And what we have represented is u minus v. Now note this isn't the only way to think about it, but I do find this to be the most intuitive way to think about it. And that finishes our discussion of the geometric perspective on vectors. In the next video, we'll pick up on the analytic perspective. So stay tuned and take care.